Okay, moving on to question 5. Question 5, we are looking at silver, forming silver halides. And you're talking about the silver halides being sparingly soluble in water. Okay, so the question asks for a precipitate forming. Okay, and we're given this very new formula that you guys have not seen before. Okay, don't panic. Alright, in A levels, if they give you a new equation, typically they'll define for you. So in this case, delta G is given as in J per mole. So some of them may be wondering why, because from all the questions that we go so far, delta G is often defined as kJ per mole. So if you take a close look at this equation, your R, it's your ideal gas constant. You're at 8.31 J per Kelvin per mole. That's the units of your ideal gas constant. You can check that in your data booklet. Alright, now with temperature is in Kelvin. Alright, so when you multiply these two units together, you end up with J per mole. Okay, of course, the natural question is what happens to log KSP? Generally, when we take a log operation of anything, log or ln, alright, this particular parameter will have no units, and that's why in the end of it, your delta G is still having J per mole. Okay, so now with this, let's take a look at the question. We are supposed to sub in log KSP. We are supposed to find silver bromide. Okay, so AgBr, let's look at the solubility KSP, right? So it's KSP, solubility product. So which value do you substitute? This one. Okay, so sub in your values. In this case, how do I know that the temperature will be 298 Kelvin? Because we are finding the standard gives you energy. Alright, so the not sign will indicate 298 Kelvin. Okay, your standard conditions. Okay, so substitute into your formula. Reminder, the units for delta G is in J per mole. Then the question wants you to express it in kJ per mole. So after that, do the necessary conversion. So you have negative 70.2 kJ per mole. So remember your negative sign. So must have sign. Okay, whether it's positive, negative, you want to put that down. Okay, moving on to part 2. Part 2, they give you the standard enthalpy change of formation. This is defined as your delta HF. So we are supposed to look at formation of precipitate. Let's look at the delta S precipitate in J per mole per Kelvin. Okay, so we are given for silver bromide. We are supposed to relate to silver bromide for the delta S. So our aim is to find the delta S. So we have the delta G, we have the delta H. Then of course, naturally, it will be quite straightforward to convert to use the equation to delta H minus T delta S. So in this case, our aim is to find delta S. So delta S units is in J per mole per Kelvin, and as a result, take a look at the approach. We'll be converting delta G and delta H into J per mole. So that's what I do over here. I multiply by 1000 to this value to convert it to J per mole. For delta G, instead of using my earlier answer, I decided to use this answer in J per mole and substitute it over here. Okay, temperature again is in 298 Kelvin because it's mentioned in the question. Work out your math, and then you end up with a 1 dP of negative 98.5. This answer may differ slightly because depending on whether you use this negative 7.015 or you use negative 70.2, some rounding off issues. Now, with look at this, you must make some sense whether this answer is valid. So in this case, what are we looking at? We're looking at the formation of the precipitation reaction, which means we're looking at the process of Ag plus aqueous plus Br minus aqueous, alright, precipitation reaction, right, to form AgBr solid. So quite obvious, from aqueous system to a solid precipitate, there will be decrease in disorder, and expectedly you can see there's a negative, there's a decrease in entropy. Entropy change should be negative. So this is actually the answer for part 3. So for part 3, let's take a look at the answer. So in this case, the sign of the answer, delta S, is negative because entropy decreases. What's the reason? If you take a look at the reason, aqueous ions becoming solid. So it's a phase change. So change in phase from aqueous to solid. And then you may want to go on to explain, alright, why is that decrease? Because when you have aqueous to solid, there are less ways for the particles to arrange themselves. The particles are more regularly arranged, less randomly arranged, and therefore there's less disorder. Okay, so that's the answer for B. We move on to C. Now for C, they give you Ag fluoride. Give you the KSP value. Okay, we use the expression in A to determine whether silver fluoride is soluble in water. So basically we make use of the same formula, sub in the KSP value. So again, notice that the G in this case will be in J per mole. Okay, because we're using the expression given A. So in A, they have already alerted us that the delta G is in J per mole. So positive value, J per mole, but that's the one that's more important because we are supposed to determine whether the silver fluoride is soluble in water. Which means, in this case, because we're looking at KSP, alright, we're looking at the formation of your fluoride PPT, right? Your Ag fluoride PPT. AgF solid PPT. Okay, so with that, the delta G as shown here is more than 0, which means the forward reaction is not spontaneous. So if that's the case, how then do we show that whether it's soluble or in water or not? So remember I said earlier on, if the forward reaction is not spontaneous, the reverse reaction will be spontaneous, which means now we're looking at silver fluoride solid forming silver ions and fluoride ions very readily. The reverse reaction, dissolution process, dissolving AgF, will be a favorable process, and therefore this reaction is not spontaneous. The precipitation reaction is not spontaneous. As a result, the backward reaction, which is the dissolving of silver fluoride, will be spontaneous, and therefore silver fluoride is soluble.